All right, we're going to start with 6.1, number 6.1. And in this problem, we're dealing with mixed columns and inverse mixed columns operations from the advanced encryption standard. And this equation comes from the text. And so the problem says, in the discussion in the text, it was stated that this equation holds where, and we're given a value for a of x here. A of x is equal to 0.03 x cubed plus 0.1 x squared plus 0.1 x plus 0.2. We're also given a value for b in this discussion, and that value for b was 0b x cubed plus 0d x squared plus 0.9x plus 0e. Okay, so one thing that we can do here is we can move this equation around a little bit. We want to use the idea of this inverse property here, and we want to show that we can use the inverse to get to do a multiplication and get 1, right? So if b is equal to a inverse, then a times b would have to equal 1. So we can rewrite an equation like this. So we can say 1 is equal to a of x, b of x, mod x to the 4 plus 1. Again, just using the inverse property. And now we can write this as a multiplication. So then it should turn out that the following equation should hold. 0e. So if we look at this as, let's just look at this like a vector multiplication, right? So our first, so this is one thing to notice. These numbers, where these numbers come from, is in the mixed columns transformation from AES. This 0.3, 0.1, 0.1, 0.2. If you remember, there's a matrix in mixed columns that looks like this: 0.2, 0.3, 0.1, 0.1. And if you remember, this just keeps getting shifted. So the next one is 0.1, 0.2, 0.3, 0.1. The next one is 0.1, 0.1, 0.2, 0.3. And the final row is 0.3, 0.1, 0.1, 0.2. Okay, so that's our mixed columns matrix. Those numbers come from here. And now we can write this also as a vector, and then we can do multiplication. So I'm going to write this vector so 0e matches up with the x to the 0 term, right? So, and that's here. I want this to happen in the first row, first column. So 0e, and then I work my way back. 0.9, 0d, and 0b. And now I can work out what this equals. And this should be row times column, row times column, row times column, row times column. I think the easiest way to do this if we pull up a hex calculator, and so for example we have to do an operation 0e times 0.2, and we can calculate that, and we get 1c, and then we can keep doing those multiplications, write them down, and then you could use this hex calculator to add them all up. But what you should find is that you will get a 1 here, and you'll get zeros everywhere else. Problem 6.9 is a similar idea. So 6.9 asks, compute the output of the mixed columns transformation for a sequence of input bytes, and the sequence is given, and then apply the inverse transformation to make sure that you get the original thing that you put in back, right? So we're gonna put some bytes into mixed columns, then we're going to take the output of that and put it into inverse mixed columns and make sure that we got that very same thing back. Okay, so the input we'll start with our, let's see, this is 6.9. So in order to do the initial transformation, right, we're going to use this same matrix that we used up here. So it's 02, 03, 01, 01, etc. This is the mixed columns matrix. And then all we want to do is we want to take the input sequence that we're given in the problem, which is 67, 89, AB, and CD. And we want to compute this. So this is a matrix multiplication. And just to, I'll just compute one row and one column. So the first, if we do row 1 times column 1, it's going to be 2 times 67 plus 3 times 89 plus 1 times AB plus 1 times CD. And then if you want, you can use the hex calculator to figure all this out, remembering that these are XORs. These pluses are XORs. And so for this one, you should get a result of 28. So you can work that out. And then when you finish this, so you'll get a vector, right? You'll compute the rest of these. So like the next one is going to be 1 times 67 plus 2 times 89 plus 3 times AB plus 1 times CD, and you'll compute that one and you get your next entry, and then etc., etc. So you'll have 4 entries here. Then you take this entire vector, we'll call this vector X, and then what you're going to do from there is page. You'll take that vector X and you'll multiply it by the inverse mixed columns matrix. So the inverse mixed columns matrix is E, 0E, 0B, 0D, 09, and then we just keep shifting this around. I'm just going to stop writing the zeros. You'll multiply here. This is that vector x that we computed on the previous page, and you'll get a result here, and what you want to do is verify that that result is the original input, which was 6, 7, 8, 9, A, B, C, D. Okay, so you verify that result. And that is, that's the gist of number 6.9. All right, let's take a look at number 8.6. This problem has to do with the stream cipher Rc4, and the problem says what Rc4 key value will leave S unchanged during initialization. So then it goes on to say that is, after the initial permutation of S, the entries of S will be equal to the values of 0 through 255 in ascending order. So in order to figure this out, we first need to look at the Rc4 algorithm. So from the text, this is on page 251, there's the initialization phase, which basically says we're going to loop through for I goes from 0 to 255, and then we are going to we're going to create this vector S. S sub I is simply going to equal I. So S sub I is initially going to be populated with the values 0 through 255, and then T sub I is going to be equal to K of I mod key length. And for this problem, we're going to let the key length equal 255, and that way T is just going to equal K. Say so T will equal K, and that will simplify things for us. So that's the initialization. Then the algorithm goes on. We set this value J to 0, and we start another loop. Now I is going to range from 0 to 255 once again. And J is going to go to J plus S sub I plus T sub I mod 256. And then we're going to do a swap. So we're going to swap S sub I with S sub J. Alright, so let's just think about this algorithm, what's going on here. Up here, S starts out with the numbers 0 to 255. And the only time S changes is down here, and the change is only a swapping of one location of S with another location of S. So at the end of it all, S is still going to have the values 0 to 255 in them. It'll just change the order. And what we want to do is figure out how to make it so that that order doesn't actually change. So if we move one step back, we see, okay, well, we're taking the ith j, right? So we're going to, I is going to go from 0 to 255. So we're going to move along S, and we're going to swap the ith component and the jth component. So again, I is just incrementing one by one, but j is changing by this. So what we need, and notice that t is in here, and t is actually equal to our key k. So what we want to do is we want to figure out what do we put inside here so that this change just goes, is always equal to I. So, okay, so we can think about what that might look like. We'll look at a few instances. So let's say, now we're working down here, so I'm talking about this I value. So if I, let's say I is going to go 0, 1, 2, 3, 4, 5. We'll look at 5 different values for I. And now we can look at what j is going to be. And remember, we want j to be the same. So j in this first instance will be, well, the initial j is going to be 0. So when we come into this first one, I is 0, j is 0. So j equals 0 plus s sub I. Well, what is in S0? That's going to be 0. 0 plus 0 plus T1, or T0. T of 0. All of this mod 256. And we need this to equal 0. So we can say right from the get-go that T0 is going to have to equal 0. Okay, let's move down to the next one. So now I is equal to 1, and we said that this T0 is equal to 0, so that this j came out to be 0. So j is going to be j, which is 0, plus s sub I. Well, now I is 1, so this is going to be 1, and plus t sub 1. All of this mod 256, and we need this to equal 1. Okay, well, we have 0 plus 1 plus T1, so we can say that we need T1 to be 0. So we can make another table down here, right? T0 equals 0, T1 equals 0. Okay, so let's continue. Now we have I is equal to 2. With I equal to 2 and j equal to 1, the new j is going to be 1 plus s2, which is 2, plus t2, all of this mod 256. Then we need this to equal 2. So we have 1 plus 2 is 3, plus t2, mod 256, and we need it to equal 2. So how do we do that? Well, if we let T2 equal 255, then we have 255 plus 1 is 256, plus 2 is 258. 258 mod 256 is 2 if T2 is equal to 255. Now, what I want you to do is to continue on from this point, because from this point a pattern will emerge, and then you can figure out what all of the key values have to be without having to calculate each one of them.